Hey guys, it's Mr. Palma. Hope you guys are having a good day so far. Hope the quiz went well. Make sure you're taking a look at the paper that you just picked up. It says resonance structures at the top. I'm going to try and walk you through it here. I'm using my phone for this because I left my iPad at school, so it's probably not going to be the prettiest handwriting, so hang in there. So basically what a resonance structure is a Lewis structure where the double bond or triple bond can be put in multiple different places. So it's basically this idea that we could have multiple successful Lewis structures, and we want to know what the real structure is. So if you'll start out by making the Lewis structure for O3 in the big open space there, O3 is ozone. So I'll just wait while you do that. Da-da-da-da-da-da. Hopefully I didn't beat you to it, but it should be a single bonded oxygen and a double bonded oxygen there to the center oxygen. Well, if we take a look at that molecule, you cannot predict which oxygen is going to have the double bond. It's going to be the one on the left or the one on the right. So we can actually draw in a double-headed arrow, and you can actually draw out the opposite structure there. That's still ozone, right? And so those would be a resonance structure, and the double-headed arrow that we drew in there indicates that those are resonance structures. So the true structure here is the big question. And the true structure here, since both structures have oxygen in them, and there's not really going to be any difference or any better structure in what you're doing, since they're both oxygens, O3s, the true structure is going to actually be somewhere between a single bond and a double bond for each of the bonds to the center oxygen. So what we end up calling it, in this case, is kind of a 1.5 bond, meaning that our oxygen is 1.5 times bonded to the center oxygen on both sides. So it's not like our resonance structure flips between being a single bond and then sometimes it's a double bond, or it's not like it's always a single bond on one side and a double bond on the other side. Instead, the strength of those bonds and the length of those bonds is somewhere between a single and double bond. Alright, so now what I want you to do is I want you to try and draw out the resonance structures for SCN1-. See if you can come up with them. I'll give you a hint that there's two valid resonance structures here. So this time, rather than me just awkwardly pausing and you can hear me breathing loud with my illness and my dog licking his butt, you can just hit the pause and draw out your own structure here, and then hit play once you got it drawn out again. Alright, so here's one structure. You got sulfur single bonded to the center carbon, and the center carbon is triple bonded to nitrogen there. I messed up. I didn't put that in the bracket. Oops. 1- charge. Yeah, that's a 1. Alright, and so you can see the double arrow, meaning this is a resonance structure, and hold your horses, and here's the other structure. And in this structure we have sulfur, double bonded to carbon, double bonded to nitrogen. Both of those structures have 16 valence electrons, just like you'd expect. So we have two valid structures for this molecule, this polyatomic ion, and we will figure out which one is the right one here in a little bit. So that's what this formal charge thing at the end of this notes is going to be about. But for right now, you can see that the resonance structure is just this idea that we can place the double bonds or triple bonds in a different place, a different arrangement to make other valid structures. And so we're going to use this resonance structure idea to talk about something else that we've previously mentioned a couple days ago and even yesterday, but haven't actually done. And that's the extended octet. So the extended octet is this idea that an octet's 8, right? Extended means bigger than 8. So some atoms can actually take on more than 8 electrons. And if you remember why we said that was It is because of the d orbitals. The d orbitals open up a lot of space for for atoms that are in the third period or lower to get more electrons. So if you look midway down this paper, I'm going to try and highlight it for you. Hey, I did it. An atom that is in the third period or below can have up to 12 valence electrons around it. So that means that these third period or below atoms are big enough to pick up enough space that they can have more valence electrons than any other atoms. That being said, you'll never have more than 12 valence electrons around that center atom. So I'm going to zoom in a tiny bit here so that we can, a little shaky. We're going to draw out the molecule SF6, sulfur hexafluoride. This is a cool one. If you get a chance to look it up on YouTube. People inhaling SF6. It's like helium, whereas helium, when you inhale helium gas and you talk, your voice is really high. SF6 is heavier than air, so when you inhale SF6 and then try and talk, your voice is really low and slow like this. So it's kind of cool to look up. But anyways, SF6 does exist. It's a common molecule, so we're going to draw out the Lewis structure for it. Sulfur has 6 electrons. Each fluorine has 7 electrons, so 7 times 6 for fluorine is 42, plus 6 for sulfur is 48 electrons in this guy. Alright, and just kind of a trick rule, if you have 6 atoms around the center atom, that tells me that everything's going to be single bonded. Because you can't fit any more electron pairs. Remember, we could only have 12 electron pairs. Each bond is 2 electron pairs. So what we're going to end up with is all single bonds. And of course, fluorine, I'm not going to draw it in for all of them, but they'd all have a full octet. So you'd have to go around and draw your bars in or draw your dots in for all the fluorines. And if you add that up, that's 8 electrons per fluorine that's on there. 8 times 6 is 48. Okay, so I lied. I did go in and draw in all the excess electrons. But you have full octets around those fluorines, and sulfur would have 6 fluorines around it. So now what I want you to do is I want you to do an extended octet for XEF4. You can hit pause here and draw it out. See if you can get it. It's an extended octet, so think about what that means. Clearly, we're going to have more than 4 pairs of electrons around xenon, the center atom. So if I draw it out with just an octet around xenon, we see that XEF4 should have 32 valence electrons. But in reality, the real molecule XEF4, Xe has 8 valence electrons, each F has 7, so that's 28, so it should have 36. So we're left with 4 too few of electrons. So what we end up having to do here is put 2 extra lone pairs on our center atom, 2 extra lone pairs on xenon. You may have been asking yourself, oh, I didn't think, xenon's a noble gas. I didn't think noble gas is bonded. Very few of them have been bonded. This is one of the few molecules they've been able to make with a noble gas. And how they were able to make it is by having xenon form an extended octet like this. So at this point, xenon would have 6 electrons around it, or 6 electron pairs, I should say. You might be asking yourself, okay, well, great, but what does this have to do with resonance structures that we talked about above? What we're going to see is that there are certain molecules that can have a valid non-extended octet and a valid extended octet Lewis structure, meaning that they could have 8 electrons or more than 8 around the center atom. So a great example of a molecule that does that is SO2. So SO2 could be drawn in a couple different ways. See if you can get SO2 with just a normal valid octet. Hit pause because I'm about to draw it out for you. Alright, so there's our valid structure with 18 valence electrons around it, and that's non-extended octet. So that's what it looks like for SO2 if you didn't have an extended octet. But sulfur is in the third period, so sulfur is actually able to get more electrons around it. So we can actually draw out another structure here that would be an extended octet. And it's actually pretty simple. So I'm going to drag this. No, maybe I'm not. I don't know what that random line is. There we go. Alright, let me draw in my double-headed arrow, because this is technically a resonance structure. So I don't know what I just said, but here I just erased a little bit, so it might be a little discontinuous, but that's okay. We're going to draw the resonance structure. That's why I drew in the double-headed arrow here. And sulfur, since it's in the third period, can have an extended octet. So what we can actually do is we can actually take one of those lone pairs up on the single bonded oxygen, and we can dump them in and make a double bond with it. So that means that both the sulfur oxygen bonds could be double bonded. It's a little sloppy, but it's alright. And both of the oxygens would have two lone pairs on them, and sulfur would have a lone pair on it. So now if we look at that as 2, 4, 6, 8, 10, 12, 14, 16, 18, still the proper number, but what we end up having there is 5 electron pairs around sulfur. We have, let me highlight them for you, 1, 2, 3, 4, 5. Right, so that would be an extended octet. Now, whereas we said earlier with O3 that there was not necessarily one structure that was right, and that it was actually like a 1.5 bond, in some cases we can actually figure out which structure is more likely, which structure is more probable to be correct. And how we're going to do that is through something called formal charge. So in order to figure out which is right, sorry, I see this now that it says now we can draw it like, there's a space for it. Oops, my bad. I put them both on the other page. Oh well. What we're going to use is we're going to use formal charge to figure out which structure is correct. And basically what we're doing is we're going to pretend like each covalently bonded atom gets 1/2 of the bonding electrons that is sharing with its neighbor. So in the case of SO2, each oxygen gets 1 of those electrons that it uses to bond with sulfur, or half the electrons it uses to bond with sulfur. And so there's a simple formula that may at first look a little more complex, but it's really not at all, to calculate the formal charge for each atom. So what you would do is you calculate the formal charge for each atom in the resonance structure. And it's the number of valence electrons that you would expect the atom to have. So for instance, oxygen, we expect it to have 6 based on the periodic table. So it would be 6 there, minus half the number, voice crack, I'm sick, that's my excuse, minus half the number of bonding electrons that we have between sulfur and oxygen, minus the number of non-bonding or lone pair of electrons on each atom. So let's take a look at this first molecule of SO2 that we drew out. For this first oxygen, we expect oxygen to have 6 valence electrons. This oxygen has 4 bonding electrons, 2 and 2. So that means that it's getting half that number. So half of 4 is 2, so we're going to subtract out 2, minus the total number of non-bonding electrons. So that's 2 and 2, so that's minus 4. And so that's equal to 0. So we'd say there's a 0 formal charge on that oxygen. Sulfur now. So for sulfur, we expect it to have 6. In this case, it has 1, 2, 3 bonding pairs of electrons. So 6 total bonding electrons. Half of that is 3. So we subtract out 3. Minus the number of lone electrons, which was 2. So for sulfur, we'd say it has a +1 formal charge. And then for this last oxygen, we have 6 is what we'd expect on it. It's only got 1 bonding pair of electrons, so 2 bonding electrons. 1 is how many it has control of, though. And then 6 non-bonding electrons. So it's going to have a formal charge of -1. Alright, so we have 0, +1, -1. You leave that on your paper. I have to erase it because I don't have any room because I can't control my handwriting on here. Okay, so here's our other structure we had. So let's start with the oxygen on the left. It's supposed to have 6. It has 2 bonding pairs, so -2, minus the total number of non-bonding, so 4. So it's going to be a 0 charge on it. The middle sulfur there, sorry, supposed to have 6 minus 4 bonding pairs and 2 alone pairs there. So it's also going to have a formal charge of 0. And then our last oxygen, 6 minus 2 bonding pairs minus 4 lone pairs. So another formal charge of 0. So how we determine which one the right structure is the one that has the lowest number of formal charge, or the formal charge closest to 0. In this case, it's pretty easy to tell. It is our second structure. And that's because all the formal charges there are 0 on it. So we would expect this molecule of SO2 to actually be an extended octet for sulfur with 2 double bonded oxygens on it. Alright, I'm going to do one quick practice with you, SO4 2- there, because you're probably running out of time in class and probably need to go. So there's actually 3 valid resonance structures for SO4 2-. Actually, there's more than 3, but there's 3 different structures, I should say. 2 of them are extended octet, one's normal. So each sulfur has 6 electrons, there's 1 of them. Each oxygen has 6 electrons, there's 4 of them. So that adds up to 30, and then it's a 2- charge, so it's 32 electrons there. Our simplest structure is to assume that everything is single bonded and a full octet. So this is our non-extended octet one. We end up with 32 electrons. We could also draw this with a double bond. So one of the oxygens could be double bonded. Sorry, for whatever reason, it's not making these bonds very well right now. If we go through there, this oxygen just has 2 lone pairs on it. All the other oxygens have all their lone pairs. So it's S with 1 oxygen double bonded, 3 single bonded oxygens. And our third option, since sulfur can hold up to 6 pairs of electrons around it, we can make 2 double bonded oxygens and the other 2 single bonded. And give them their full octets. So to figure out which one's right, we'd have to go through each structure, calculate the formal charge for each structure, and then figure out which one's closest to 0. You do that now. I'm going to tell you the answer here in a second. Hit pause. And so if we look at these, the formal charges on them, if you notice, they're all going to add up to -2. That's because the overall charge on SO4 is 2-, so there's 2 extra electrons gained somewhere. The first structure, everything has a formal charge. The second structure, only 1 oxygen has a 0 charge, everything else has a formal charge. And the third structure, 2 oxygens and a sulfur has a formal charge. So this ends up being your right structure. And your winner, chicken dinner. So that means that sulfur, sulfate, should look like this, and there should be a bracket around it, of course, because it is a polyatomic ion. Alright guys, try the homework the best you can. I'll be back on Monday, and we can talk about it then. Have a good weekend.